I'm recording this meeting and going to talk about the phonons. All right. So, I'm just today going to start with quantization of elastic waves. And the book I have already given to you, this Charles Kittel, and that is the book which I'm following in this lecture series. Okay. So we we already have an idea that in a crystal we have different modes of vibrations. Different modes of vibrations means actually uh, frequencies starting from 0 to certain maximum. So this maximum frequency is limited by our lattice constant, as we have learned in this dispersion relations, that lattice, due to this minimum length or discontinuity of this elastic medium at a small length scale, we have a minimum wavelength or a maximum frequency and maximum wave vector. So as you can see that this in this diagram, I have shown this different elastic waves with different frequencies. This is a smaller frequency or large wavelength, and this is a larger frequency or a smaller wavelength. So there is an entire spectrum of that actually, starting from 0 to certain maximum. Now, when you have a spectrum of these frequencies, so one of the frequency for which you see here, that is called a mode of vibration. So let us say this is omega 1, and another frequency is omega 2, and another is omega 3, like this. So these are different modes of vibrations of your elastic medium. And now the energy of each elastic mode can be quantized like this. You have already solved the equation of a harmonic oscillator in quantum mechanics, and you know that energy is quantized, n plus half h cross omega, where half h cross omega is called 0 point energy, and n is equal to 1 is first excited state and second excited state, and like that. So this is the quantized energy spectrum. Just like in case of electromagnetic radiation, the quanta of radiation is called photon. Here, this quanta of energy of elastic wave is called phonon. So it comes from the word phonetic, which means sound. So just like a sound wave also has an energy, and it has different modes of vibration. So each mode of vibration is basically a harmonic oscillator, and its energy is quantized, and each quanta is known as the phonon here. Okay, so that's the idea of phonon in elastic waves. Now let's read this phonon momentum. It says a phonon of wave vector k will interact with particles such as photons, neutrons, and electrons as if it had a momentum h cross k. So, however, a phonon does not carry any physical momentum. So this you have already seen in case of Compton effect, that a photon actually interacts with the electron as if photon is having a momentum h cross k, or k is 2 pi upon lambda there. So this is also true for the phonon, because it is a massless particle. So in that sense, it does not carry a physical momentum, but it behaves as if it carry a momentum h cross k, and momentum conservation laws can thus be valid here. So now let's come to this equation, and you see this equation, elastic scattering of a X-ray photon. This equation which you see here is nothing but it's another form of Bragg's law. In a Bragg's law, you know that 2d sine theta is equal to n lambda. That is what you are familiar with. And I think you are not familiar with this kind of formula, but this is an equivalent formula for that. So this G is a reciprocal wave vector, K is a wave vector, you can say incident wave vector, and the scattered wave vector, and G is the reciprocal lattice vector of particular crystal on which this photon is incident. So then the change in the wave vector is proportional to the lattice vector. So now here the change is not in the magnitude but only in the direction, and this kind of interaction is called elastic scattering, where magnitude of k is not changing here, it's only the direction. This equation is a vector equation, so you should understand that if you take the magnitude of k dash and k, they come out to be same. Okay, so this is case for X-ray photon. Now uh, let us talk about the interaction of the elastic mode and a photon. Let us say some of the photon, X-ray photon, is incident on a crystal, and the crystal, let us say, is propagating some sound wave, or you can say this is an elastic wave. So naturally, it will have some distribution of phonons in the system, and these equations represents here the inelastic scattering of phonons. Here, this is the inelastic scattering equation. Just here, it was a case of elastic scattering because the energy remains conserved here, because k dash is k. The magnitude of k dash is equal to k. Here, you see this k is a momentum of incident photon. G is a reciprocal lattice vector. K dash is a momentum of outgoing photon. So this is, remember, a photon. This can also be a neutron. So you can have a neutron beam or a photon beam incident on your crystal. So if it is a neutron beam, then this K is for neutron, or otherwise it's for the photon if it is photon. And this capital K, which you see here, this is the phonon wave vector. This is the phonon wave vector here. So the equations of the momentum conservations are like this, that if in the interaction one phonon is created, so this plus sign means one phonon is created here. This means your this elastic vibration mode is excited. It goes to, if it was at n is equal to 1, it goes to n is equal to 2. So now there is a one extra creation of a phonon into the system, if plus. If it is minus, then it is an absorption of phonon. One of the phonon disappears from the system. So this is a momentum conservation of interaction of photons with the help of phonons. And phonon can also be thermally generated, because at any given temperature, you know that there are atomic vibrations in the system. And atomic vibration basically means you have elastic vibration in the system. And for a given mode of vibration, you will have a corresponding phonon spectrum. And that is quantized, or you will have different phonons in the system. Now, here, this is the same equations with the energy conservation. So this is um, with respect to neutron. Here, Mn is the mass of neutron, as you understand, that this is the energy of the incident neutron. This is the energy of the outgoing neutron, and this is the energy of the phonon. So if a phonon is created, it will have an energy of h cross omega. If phonon is absorbed into the system with the minus sign, it is absorbed, then uh, this energy will be lower actually. You can see that. So you could see that here the energy of the outgoing uh, neutron or photon is changing depending on, if let us say, I suppose this is the energy of the outgoing photon. No, this is actually the incident energy. sorry, the energy of the incident neutron or photon. This is the energy of the outgoing neutron or photon, and this is for the phonon. So you can see this is a constant. So then now k dash has to be smaller than k now, and that is why this is inelastic scattering. Now magnitude of k and k dash are not same here because some energy is created in the form of phonon, or it is absorbed. So you will have either higher energy k dash, or you will have a lower energy uh, with the lower k value. So lower k value or higher k value. So this is energy conservation equations, and this is momentum conservation equations. Okay, here k is the wave vector of the phonon created plus and absorbed minus in the scattering process, and g is the reciprocal lattice vector. For a phonon, we choose g such that k lies in the first billion zone. So we always talk about first billion zone. Now let's say how to experimentally find out this dispersion curve. So this is in a first billion zone, this is a k and this is omega. So dispersion relations are always like omega and k. So how one can measure this? These are different directions, 0, 0, 1, 1, 1, 0 and 1, 1, 1. So in different directions, these and this is a longitude, and this transverse waves is for the this solid is for the longitudinal wave, and open is for the transverse wave. That is how this are plotted. So what a new people in the measurement do is that they measure the energy of the incoming neutron and outgoing neutron, and they can see that when this phonon is absorbed into the system, uh, one phonon is created into the system, then this will have less energy because their summation has to be equal to this one. And if one phonon here is absorbed into the system, so the energy of the neutron has to be higher, uh, so that this is equal to right hand side. So it is not very difficult to know the energy of the incident neutron, because these are called thermal neutron. And at thermal neutron, we know their energy. It will be half kT, let's say, and we know the temperature. And if we know the energy, so at any given temperature, energy of the neutron beam can be determined. And here we have a detector with the help of which we measure this energy of the uh, outgoing neutron after scattering, and their difference tells us the energy spectrum. So this equation is written for a single mode. Let's say there are different kind of frequency mode into the system. So for a given mode, this much change will be there in the energy, and this omega is variable because there are different modes of vibrations, and so h cross omega will be a continuous thing. That is why you can see that it is continuously varying here. So this is the frequency, and that is how we find the dispersion relation of phonon omega versus k with the help of neutrons. So this is a picture of our chamber. There is a nuclear reactor here, and the neutron beam is coming from there. So when you want to do a study with the neutron, definitely you will need very big installations, and a nuclear reactor somewhere where you can produce the neutron in a reaction chamber, and then you can make the beam of them and use them for the purpose of dispersion relations. So in India, we have definitely that at Bhava Atomic Research Center in Mumbai, where we have nuclear reactors, so we can produce a beam of neutron for the study of this dispersion relations. So in the world, they are everywhere. In all advanced laboratories, we can have a neutron beam and study the dispersion relations. Okay, so now I will come to another important aspect here. I will be just going slow, and we'll understand this. because this is what we are going to drive now here. It's going to play a role, or we will use it in description of the specific heat. So we will introduce a concept of density of states. So first we will talk about some boundary conditions, and based on those boundary conditions we have some densities of states in one dimension and three dimensions. Real systems are three dimensions. So our ultimate aim is to actually find out density of states in three dimension, but we start with the one dimension so that we can simply understand the idea of the density of states. So here you see this is the figure. um, Consider the boundary value problem for vibration of one dimensional line of length L carrying n plus 1 particles at separation A. So this is the one that one particle is placed here, another here like this, and you have S is equal to up to 10, and the separation between these particles is A. This total length from here to here is L, and this is the one dimension case. So they're free to vibrate in the transverse mode like this, or longitudinal mode like this, and the ends are fixed. You fix S is equal to 0 and you fix S is equal to 10 here. You have bound it. It's just like a string. You take one string and just bind it at both the end, and then allow it to oscillate by pulling it at one end. And you can see you can generate different kind of wavelengths in the system. So this is the system where you have atomic spacing also. So this is, let us say, some atoms which are placed at a definite time interval. And in such a system, two ends are fixed here. So this atom cannot move at S is equal to 0, and this atom at S is equal to 10 cannot move. So basically, if you have n atoms, or these are n plus 1 atoms, you will have n minus 1 atoms which can move, because two atoms at the end cannot move. Okay, so uh, now this says that we suppose that the particles S is equal to 0 and S is equal to n at the ends of the line are fixed. Each normal vibrational mode of polarization P has the form of a standing wave, where US is the displacement of the particles. Now here one term is coming, one is the polarization and another is a standing wave. I hope you understand the meaning of it. Polarization here means uh, this one wave can have two transverse components. Suppose this is x direction, so it will have y and z transverse oscillations and one longitudinal oscillation. So basically there are three states of polarization here, two transverse and one longitudinal. So this is what they mean by polarization. So each normal vibration mode, so each mode means if you have a given frequency mode into the system, it can have three polarizations, two transverse along x direction, y direction, and one longitudinal along z direction. Has the and form the standing wave, and the displacement of each particle is given here. So this is the standard solution. Okay, when you are talking about a standing wave, it means because these ends are fixed, the wave reflects back. If a wave is traveling like this, it will reflect back here, and it will form node and antinode, node and antinode. So there will be um, one wave propagating this way, and because this end is fixed, now it cannot propagate, it will reflect back into the system. That is what we call a standing wave. When you fix the ends of a string, it will always form a standing wave. Okay, so this is how we can understand this. Only when you let the string free, it will propagate in the forward direction. So when you have a standing wave solution, you always have this it is in the form of sine sk, because you will have exponential uh, I kx and plus minus I kx, because the wave is moving in x direction and minus I direction, and so exponential kx and plus exponential minus kx or minus, they can either be written in the form of sine or cos. It's your choice. You can write it in form of cos also. So here it's better to write it is in sine form because it suits our boundary conditions. And that's how we will understand how the solution. Now, in case of omega, uh, because this is a time variable here, k here is telling us the particular mode, and p is a state of polarization of this system. That's how they are numbered. So this is a solution which is telling us the displacement of any atom at any point S. Okay. Now, what we do at the boundary, we know that this is 0. US is equal to 0 and U0 is equal to 0 because both the atoms at the boundary are fixed and they are not moving. So if you put that 0 here in this equation, what remains is this condition here. And this gives you n pi upon x. Sorry. This n pi is kx. So, and x is nothing but it tells you your total length from here to here, which is L. So this is L, or if you would like to write in terms of lattice constant, this is SA. So basically now here your n can have values 1, 2, 3, 4, 5 to satisfy this boundary condition where endpoints, the displacement of the endpoints is 0. Okay, so in that sense, if you pick up from here, it tells you you have pi upon L. If n is equal to 1, if n is equal to 2, you have 2 pi upon L. These many values are there. And then you will have, this will go up to n minus 1. So it is telling us that actually that many number of modes, vibrating modes are possible into the system as the number of free atoms. The number of free atoms here are n minus 1. So there are total n plus 1 atoms. This 0th atom is fixed and n plus 1 atom is fixed. So what remains is total n minus 1 atoms which are free to move. So these are n, there will be n minus 1 modes into the system. Now you may think that why I have restricted this to n minus 1. You can go into n, n plus 1 and all. Mathematically, there is no problem. You can satisfy this equation even if you go to a higher value of n, n plus 2 or n3. It will always satisfy in mathematical way. But we understand in terms of physics that and we know the idea of degree of freedom. So the degree of freedom are determined in the system by the number of particles the system has. So here you have n minus 1 particles which are free to move. So there will be um, n mode of vibrations into the system, n minus 1 modes of vibrations of the system, because equipartition theorem tells us that each mode will possess half kT energy. So this is a physical requirement that we keep our mode of vibrations up to the same as the number of vibrations, as the number of atoms, free atoms into the system. Now you can think if this is a problem in one dimension, if you take this problem in 3 dimension, so if there are n particles into the system which are free to move, there will be 3n degrees of freedom because each particle is free to move in 3 dimensions. So then this becomes, now we are saying it because we are talking about just one dimension problem. We are thinking that motion is possible only in one dimension. Okay, so now here the diagram which you see here, these are in a K space. It is not the same figure as you saw last. This is in real space. You place your atoms and this is the real distance. This is a wave vector space here. So each dot here tells you pi upon L, which is to 10A because there are 10 atoms into the system. And the total length is up to the 10A here, 11 atom is there, sorry, into the system. And then 2 pi upon like this. So these, each state here is actually a mode of vibration. It is telling us that system can vibrate with this mode of K, and K means it will definitely have some frequency. And we are going into higher value of K means we are also going into the higher value of frequency. So you have this frequency or wave vector mode of vibration, you have the next mode of vibration. So these are different modes of vibrations. And you can see here also you have n minus 1 modes of vibrations. So if there are 11 atoms, you have n minus 1 means 10 modes of vibrations into this system. So that's how it is easy to understand that this figure is made in the reciprocal space, and this is telling us how many modes of vibrations are there into the system. So if there are 9 atoms free to move into the system, so there will be 9 modes of vibrations. Now, I hope I'm going slow because that we have to understand this. Okay, now let's read this. This, so you see, I have just copied from Charles Kittel, so you can refer just directly the book of Charles Kittel, which I have given to you. You can read from that, and now it says, come to this line where my cursor is. The solution for k is equal to n pi l is equal to pi a. K maximum has us is equal to sine s pi. This permits no motion of any atom because sine s pi vanishes at each atom. So let us say instead of n minus 1, if we put n here, what happens? This n upon l corresponds to a. And this is, you reach at the extreme atom and which is not moving. So then it does not correspond to any mode of vibration. So just before that, if you have n minus 1 here, so those modes are actually allowed into the system. Thus there are n minus 1 allowed independent values of k. This number is equal to the number of particles allowed to move. So the number of modes here, it is important to understand, the number of modes are equal to the number of particles allowed to move. If you have 10 particles in a system which are allowed to move, you will have 10 modes of vibrations into the system. And this is in one dimension, remember, we are talking about one dimension just only here. Now, each allowed value of k is associated with a standing wave. For the one-dimensional line, there is one mode for each interval delta k pi upon L. So the number of modes per unit range is L upon pi for k less than pi upon A, and 0 for k higher than pi upon A. So it is, now we are going to count, as we are going to talk about the density of states. So the number of modes per unit range of k is L upon pi. How it is, just we can understand it from the last figure, not very difficult. Let us say, if I want to say, what is the length of uh, from here to here, from one point to the another point in a k space. This is a k space. Though, so the separation of 2 points in k space is nothing but pi upon L. This we know already. Okay, this sorry, this is telling us that in k space this is pi upon L, 2 pi upon L. The separation between 2 points is basically pi upon L. If we put our boundary just in the middle of 2 points here and just in the middle of 2 points here, so we are taking half of this distance and half of this distance. So that will again be pi upon L. So if you take distance from the midpoint of here and midpoint there, it will again be pi upon L. If you have a separation of pi upon L between each mode here, so if I put my bar in the middle of this bond, this will again be pi upon L. So I can say that corresponding to each point, this much length is there. So for a given point, for all points, you can see that in a pi upon L length, there will be 1 point. After every pi upon L length, there will be 1 point. So how you want to find out the particle per unit length? So that's how you do that, number of particle divide by length. And in this range, there is one particle and length is pi by L. So 1 by pi by L, so it becomes L by pi. So if you do 1 upon pi by L, 1 upon pi by L, so L goes above, so it becomes L upon pi. So number of points per unit length is basically L upon pi, which is here. Okay, because this comes from 1 upon pi upon L. L goes above, and you have just the number of modes per unit range of K. Now that's the question we are asking, that is L upon pi. Okay, now let's say there are three polarizations P for each value of K that we have understood. Two transverse polarization and one longitudinal polarization. So there are three polarization possible for a given value of K. Okay, in one dimension, two of these are transverse and one is longitudinal. In three dimensions, the polarizations are this simple only for wave vector in certain special crystals directions. Okay, so three case of three dimension we will talk about later. So that was a given boundary condition, and that was a fixed boundary condition we call. We have understood there um, that the number of modes of vibration will be equal to the number of free particles to move into the system, and the we can say uh, the number of modes per uh, unit range of K is L upon pi. So these two things we understood from there. Now this is another boundary condition. This is called periodic boundary condition, as you see in this figure. Um, Here, another device for enumerating mode is equally valid. We consider the medium as unbound, but require that solution be periodic over a large distance L. So you see, as you take some, let us say, crystal, and the atoms inside the crystals are allowed to vibrate, move, though they are bounded with their surrounding atoms, but still they are free to vibrate. And atoms at just at the boundary of the surface, they're also free to move. Okay, they are not bound in that way. Surface atom can also vibrate on any of the surface. So here, instead of having atom fixed at the end, now these atoms at the end point are allowed to move in this particular boundary condition. This is called periodic boundary condition here, and we can easily make it into a circle. This is a one-dimensional case again. Remember, we are talking about one-dimensional system. So we put S is equal to 1, S is equal to 2, and we are going to put atoms in a circle, and each atom is separated by length A. So after some time, we come back at the same atom. So this is like this, that if you have one atom at one side of surface, it will be moving, it will have same environment as the atom on the other face, degree of freedom, because this also is bound from three side, and on the opposite side also it is bound from three side, and they will have identical motions. So in that sense, we can say, we can connect these two ends together, and we can say that this atom at one end is vibrating, having the same amplitude at the atom as the atom at the other end. So it is easy to connect this into a circle, and that's why it is called circular boundary condition. So this is the idea, and the boundary condition is this here, that you see the entire distance is L again here. All atoms are allowed to move. So USA is equal to USA plus L. Now here you can take any atom as S. Let us say if you start from here. So again, if you move by a distance of L, because this is L, you come back to the same atom here. So this displacement of this atom has to be equal to this atom. So because we are standing at the same atom itself. So if you do that, if you apply this condition, now here you see that in this solution, you do not have a sine term. Both are exponential, ska omega t, because it's a traveling wave. There is no standing wave in such kind of system, because ends are not fixed. And when ends are not fixed, when wave is propagating, let us say in a direction, it will keep propagating in that direction only. If it's propagating in this direction, it will keep propagating in this direction. So there are no fixed atoms. So there are no standing waves here, just a propagating wave. That is why instead of taking sine here, We have taken an exponential I K S A. And when you satisfy this boundary condition, uh, then what you get is this, that value of k is equal to 0. Um, now I request you to satisfy this boundary condition, because ये जो SA है यहाँ, take x here. Better you write XA instead of SA. Okay. And once you used x is equal to 0, because you are at 0, and another time you use x plus L. So this is x plus L. And this you have to keep equal. And then what you get from there is those allowed values of k. So if you have that boundary conditions, these values of k is equal to 0, 2 pi by L, 4 pi by L, 6 pi by L, plus minus. So here I want you to do it with your pen and paper, that this is the boundary condition and this is the equation for you. And if you do this boundary condition, do you get this allowed values of k? So I just give you a 5 minutes. You have your pen and paper, and just I would like you to derive it here. It's very simple. Exponential, you put both side here, USA. Instead of SA, you can take X. That would be better. Instead of SA, you can take X, and you can do X plus L. So it would be easier that way. So I just give you 5 minutes. Now it is 11:40, 11:45. I will come back to ask you if you got this values of k same applying this boundary condition. So just I want you to do that. So I'm just stopping for 5 minutes. I'll be back, and I give you this time to complete this. So I'm leaving this uh, screen open so that you can see it and do it on your paper. And when you just send me message in a chat that you have done it, then I will proceed further. So when you have done it, you can just raise your hand and show how you've done that. Okay, so somebody raised hand. It seems that Ashish Kumar have done it already. It is simple. I think I can just show you putting on my camera that actually it is possible. Now you can see this. I've just done this. Can you see this camera if I make it bigger? Okay, I'll come back to this. Maybe I just if you I have, you can see that it's very easy. It seems that Phonons, what I was doing, yeah, here it is. Okay. Okay, Ankit Dhiman raised hand. So many of you have done it. It's simple. Good. I think now can proceed and see the idea is simple here. You can forget about I omega t because there is no boundary condition in time. So in both side, this term will cancel. Exponential I omega t on this side and this side, they will cancel. Only it will remain I kx on this side. On another side, it will be I k x plus L. And ikx will also cancel on both sides. So on one side, you will have 1 ikl, and then 1 is equal to exponential 2n pi I. And that because that is cos theta plus I sin theta. And if you equate that, you get this. So this is another periodic boundary conditions where the separation in K space, remember this is K space, the separation in K space is 2 pi by L. Earlier, in case of fixed boundary, it was pi by L, but in periodic boundary condition, this is 2 pi by L. Separation between each mode of vibration. So here again, these are not atoms, but this point represents different modes of vibrations. And here it is not n minus 1. It is the um, how many number of points you have is equals to the same number of modes of vibrations you will have into the system. If you have n atoms, you will have n modes of vibrations because no atom is fixed here. All atoms can move. So you will have all modes of vibrations possible here. Now, okay. Um, now, similarly, if you just would like to know, this method of enumeration gives the same number of modes per mobile atom as given by equation 12, but we have now both plus and minus values of k with the interval. Now here your wave can travel in clockwise direction and anti-clockwise direction, so you will have both plus and minus values of k here, and the interval between each mode of vibration is 2 pi by L. So delta k, the interval between the points in k space is 2 pi by L. Now again, you ask the same question for a periodic boundary condition. For periodic boundary condition, the number of modes per unit range of k is L upon 2 pi. So here this 2 pi by L will be L upon 2 pi, because what you will do again same thing, that I want to find out that in a unit space, how many number of modes are there per unit length. So you choose the unit length as the separation between these 2 points. And now if I put the marker in the half of each, this distance is again 2 pi by L. So there is a 1 point here, one number of points, which is 1 divided by 2 pi by L, and L goes on the top. So it gives us the number of modes per unit range of K is L pi by 2. So how many number of modes are there in a unit range of K? That is what it is asking for. So it just becomes reverse of this. If you ask this question, the number of modes per unit range of K for this first billion zone, because that's the maximum you can go, and zero otherwise. Outside this range, there are no modes of vibration. So all modes of vibrations are there within the first billion zone. The situation, okay, two-dimensional lattice, let's not talk about this. So now here we define a term called density of states. So I will just stop after this. I will just tomorrow come back to the lattice specific heat, because that is what I want to talk. And it was necessary to introduce you the idea of these two boundary conditions, which is fixed boundary condition where both ends are fixed, and periodic boundary conditions where all atoms can move. So now here uh, you can read this. It is already there in your Kittel's book. From there I have taken it. So we need to know d omega, the number of modes per unit frequency range for a given polarization. The number of modes d omega in d omega at omega is given in one dimension by, so this is a one-dimensional problem. We are talking about one-dimensional problem. It is saying that in this frequency range, because you have an omega and you extend omega plus d omega. So in this given frequency range, how many modes are there? Now we are counting this number of modes. So when I say this is the density of modes, so density, so this tells us the number of modes in a, we are counting the number of modes in a given range d omega at any frequency omega. So this is simply the multiplication of number of points per unit range of K multiplied by dk. Now this dk um, spans the corresponding range in the wave vector space, which corresponds to d omega. I mean to say that as K is changing, your omega is also changing. This is in frequency domain and this is in wave vector domain. So when we say d omega, it will have its corresponding dk. This is the extension in frequency space. The corresponding extension in wave vector space is dk. So actually this d omega cancels d omega. So you can understand this is basically nothing. We learned that in a fixed boundary condition, L upon pi is a number of points per unit range, and then now you multiply it by the range. So you get the total number, total density. So that is the idea. So when you have this d omega upon, you can multiply d omega here, d omega there, and so that's what you get, d omega upon dk. Now this is very easy. D omega dk is very easy to find from any dispersion relations, because that is what we get, and this is group velocity d omega upon dk, and put it here, and you can find out the number of modes in a given frequency range from omega to d omega. So this is just in one dimension. This has been described in one dimension. We will just in real problem take this further in the 3 dimension. Till now you understand this concept, how it is coming. It is very simple, it's very ordinary. Just you have to apply your logical understanding to it little bit, and just not difficult to understand how you get there, because this is not anything coming from some derivation of the formulas or some scientific assumption. This is just some algebraic terms. How can you write if you ask your question that how many number of particles are there? Let us say it's just like this, that if I know the density of the system, copper, then in 1 meter cube, how many, what is the mass of 1 meter cube? This I give you the density. So you multiply density by volume and you get the mass. So it is just like that. Now situation here is one dimension, and when you say volume, here volume does not exist, because in volume you have 3 dimension. Or if you want to say volume of the system in 1 dimension, this is length. Length is the volume here, because the system is 1 dimensional. So then you forget about all 2 dimensions. So your length itself is a volume, you can say, in 1 dimension case. Okay, so we can obtain the group velocity from the dispersion relation omega versus k, and this is a singularity whenever the dispersion relation is horizontal. That is okay. This we will talk about later. It's not so important. So that's what idea is, that we want to write it like this, because this d omega upon dk we can easily find out from the measurement and can understand the density of the states here. Okay, so what gives us the number of modes? How can we count? You know the length of system. This is L. It depends on that. So if your system is 2 centimeter long, so this will be 2 centimeter in that units divided by pi, and the same range, whatever it is, and divided by the group velocity. That is how you can get the number of modes. That is how you can count them. So I just end here. Now density of states in 3 dimension, I will start tomorrow. And from here onwards, I will talk about some phonon specific heat and all these things. So I just stop here today. And you learn these concepts, which I have told you today. This is fixed boundary condition and periodic boundary conditions. And what I have discussed with you, you have this book of Charles Keetle. You just do little exercise and we'll come back tomorrow. Okay, so this is okay. Now it seems I have. Okay, so I'm waiting for your questions if you have any at this moment. So, all right, I'm going to end this now, and I will send you the recording of today's lecture, and then you can revisit these concepts of this boundary conditions, fixed boundary conditions, and periodic boundary conditions. Once you understand it, you have to sit with your pen and paper, nothing difficult, and then the next, which the ideas which we are going to put forward, you can easily. Yes, it seems Yasin Bhatt wants to say something. Yasin, you want to say something, Yasin? Okay, no, okay, great. So now let's say end meeting, and bye bye, and thank you for watching.